Electric vehicles might feel like modern marvels, but the engineering puzzle behind them is over a century old. Take a look at this photo. That's Thomas Edison standing next to an early electric car, showing off its massive open battery compartment. The core challenge he faced is the exact same one we face today. People often assume that charging a modern EV works exactly like plugging in a massive smartphone, or simply swapping a liquid fuel nozzle for an electric cable. But that analogy hides the physical reality of the process. The core issue is a basic electrical mismatch. The power grid operates on alternating current, or AC, represented here by this continuous rolling wave. Vehicle batteries only store direct current, requiring a rigid, flat delivery. Therefore, an EV charger functions as a translation engine, catching the rolling AC wave and physically forcing it flat, rectifying it into direct current before entering the battery. Where exactly this electrical translation takes place dictates everything else about the vehicle: how fast it charges, how big the station needs to be, and how much heat the system must dissipate. When you plug an EV into a standard residential wall box, you're using level 2 charging. That box on your garage wall acts merely as a smart, secure conduit piping raw grid power directly to the car. Because the vehicle is receiving alternating current, the actual translation into direct current happens deep inside the chassis, within a component called the onboard charger. This creates a harsh engineering constraint. The onboard charger has to ride inside the car everywhere it goes. If engineers make this converter too large or too heavy, it will constantly drain the battery just to carry its own weight down the highway. Because of these strict physical limits, the conversion rate is deliberately throttled. Most onboard systems max out somewhere between 3.6 and 22 kilowatts. That is why residential charging typically takes all night. Home charging intentionally sacrifices charging speed to protect the vehicle's overall driving range, supplying a slow trickle of energy rather than a fast flood. But a slow trickle doesn't work on a road trip. When drivers pull up to a highway station, they expect a massive, immediate transfer of power. To achieve that speed, engineers use a brute force workaround. They remove the conversion electronics from the car, housing them inside massive standalone charging cabinets. By completely bypassing the vehicle's internal hardware, these stations can pump pre-rectified high-voltage DC directly into the battery pack, pushing anywhere from 50 to well over 350 kilowatts of power. Pushing hundreds of amps through a cable generates electrical resistance. Because heat generation scales with the square of the current, even a tiny amount of resistance converts energy into waste heat at a rate that can quickly overwhelm the charging hardware. Look at these safety warnings from a reference design. If the hardware sensors detect temperatures approaching 55 degrees Celsius, the system triggers thermal derating. It automatically slashes the charging current to prevent the components from reaching a critical failure point. Without a way to control that heat, pushing high power forces the system to throttle itself, doubling or tripling the wait time and defeating the purpose of a fast charge station entirely. To solve this thermal bottleneck, we have to look past the thick cables and large cooling fans down to the microscopic power electronics solving the problem at its source. Wide bandgap semiconductors, specifically silicon carbide and gallium nitride, provide the physical foundation for modern fast charging. Engineers use these materials to replace standard silicon chips because they can handle significantly higher voltages and possess vastly superior thermal conductivity. This top-down view shows a reference design board for a charger. Silicon carbide allows the switches on boards like this to operate at incredibly high frequencies. They convert electricity with almost zero energy loss, allowing systems to reach up to 98.6% efficiency. By utilizing advanced circuit layouts, like bridgeless totem pole power factor correction, engineers entirely eliminate older, lossy components, like traditional diode bridges. This strips away massive amounts of conduction heat from the translation process. Preventing heat from being generated at the semiconductor level is the first critical step in allowing these high power stations to operate safely without internal damage. Even with highly efficient chips, mechanical thermal management is still required. Fast chargers rely on active liquid cooling loops running continuously inside the charging cables themselves. This circulating fluid strips heat directly off the internal copper wires. That allows the cable to remain thin and light enough for a person to handle comfortably, while safely carrying massive electrical currents. We will need every bit of that cooling capacity. The upcoming megawatt charging system standard, designed for heavy long-haul logistics, will push an astounding 3,000 amps, testing the absolute physical limits of these electronic and thermal systems. An EV charging station is never just a plug. It is a highly advanced, carefully orchestrated energy conversion facility that makes the electrified future physically possible.